Our screen recording for lesson 2.1 Basics of Motion, where we look at the fundamentals for motion and kinematics in physics that will be needed to study many more complex and advanced concepts within physics. So many of the stuff we'll look at today is mainly just definitions and concepts. They may seem quite mundane and unimportant because of how subtle they are, how subtle the details and distinguishments between what we're looking at today are. But in reality, this is probably perhaps the most important lesson in all physics, because if we do not get these basics down, then there's going to be a snowball effect that will make the rest of the course much more difficult. These basics right here will appear over and over and over again throughout the year, so it's important we have a solid basis. So here's a check for prior knowledge if you want to do at home. Alright, classify the following as true or false. Speed and velocity describe the same physical concept. Or B, an object can accelerate by changing direction. Okay, true or false if you so desire to do so at home. So again, we're looking at basics of motion today. Announcements, please disregard these announcements. These announcements are not updated for the current year. As I have lacked internet connection over the past week, I was not able to update these announcements in the moment. So we're up to today, learning the basic quantities by which we describe the motion of an object, discovering different ways that we can visually represent the motion of an object, and applying mathematics to model the motion of an object. So true or false, a train starts in downtown Phoenix and travels a distance of 400 miles. The object is now 400 miles away from Phoenix. Is the statement true or false? Would you trust it with your life? Would you put all your life savings and put yourself out in a lightning storm saying that's true for this statement here? So let's take a look. So it sounds like it certainly could be true. We travel a distance of 400 miles. We have to be 400 miles away from Phoenix. But there are some other possibilities we could have. It could be true or false. So it is true that our object could be traveled 400 miles north, south, east, or west, or a combination of those directions from Phoenix. The object could travel 400 miles east and then 100 miles west, all right? Or perhaps better said, 300 miles east and then 100 miles west. So we travel an overall distance of 400 miles, but we end up 200 miles away from Phoenix. Or the object could travel 200 miles south, all right? And then 200 miles north. Again, I don't know what's up with my numbers here. I must have messed this up or I must have changed the slides. But we can go 200 miles south and then 200 miles back north, so we travel a distance of 400 miles, but we'd be right back to where we started, right back in Phoenix. So this forms a basis for what we call distance versus displacement, okay? So total distance an object travels is not the same as its change in position from where it started. Displacement considers the change in position x of an object. It is measured in meters, okay? So, we represent position letter x in physics, like x marks a spot on a map, okay? So distance strictly considers how the length of path you traveled. Say we take this path right here from a start point to an end point, the whole length of this path represents our distance. Distance is like the odometer in a car. The odometer in a car does not care about where you're heading or where you go or your direction. The odometer in a car is simply going to keep track of how many miles you've traveled, okay? Displacement, on the other hand, measures at the end of the day how far you end up from your original position. So displacement does take into account direction, because if we want to know how far we end up from our original spot, we not only need to know how the length of path between where we started and where we ended, but we also need to know our direction. Are we southeast, northwest, west, or southwest, so on and so forth, okay? So displacement is given by the equation displacement equals final position, what we represent with xf, minus initial position, xi. Okay? The idea here is that displacement is represented by this symbol called delta x. Delta is a symbol in math which means change in, and x means position. So displacement means change in position is represented by delta x. And again, as we've talked about, distance is independent of direction. Again, like the odometer in a car, we do not care about which way we head with distance, while displacement does consider direction. So let's look at some examples here. What is the distance traveled for path C, and what is the displacement for path C? Okay, so if we look at path C right here, we see that for a distance traveled for path C, all we're going to do is count to the length of this path right here. So from 2 to 10, path C has traveled a distance of 8. From 10 to 8, path C has traveled a distance of 2. And then from 8 to 10, path C has traveled another distance of 2. So overall distance traveled for path C is going to be 12. Okay? The displacement for path C, however, is going to be the difference, aka the change in from our final position to our initial position, or excuse me, from our initial position to our final position. So we're going to go from 2 meters to 10 meters, okay? So that means our final position, 10 meters, is going to be subtracted by 2 meters, our initial position. So our overall change in position is going to be 8 meters, the difference between 10 and 2. All right, so we're going to end up 8 meters to the right of where we started. Let's look at object D down here real quick, because D is quite interesting. If we calculate the displacement of object D here, okay, object D is going to start at 9 and it's going to end at 3, so the displacement is going to be -6. All right, our final position is 3, our initial position is 9, so our change of position is -6. Why would we get a negative number here? Well, the idea here is that our object has ended up to the left of where it originally started at, so as a result, our displacement is going to be negative. The negative sign in physics tells you which direction your object has headed or is heading. So negative sign here in this case, -6, means that we've ended up 6 meters, 6 representing how much we moved from our original spot, to the left, the negative indicating that our object is ended up to the left of where they've initially started, at the 9 meter mark. So next we get up into speed versus velocity, okay? So speed, which has units of meters per second, is defined as the rate at which distance changes per second. So speed is distance divided by time. Velocity, on the other hand, is a little bit more subtle. Velocity, which has the same units of speed, is defined as speed with direction. It is defined as the rate at which displacement occurs per second. So velocity is defined as our displacement divided by our time, okay? This is quite weird to think about because we usually associate speed and velocity with the same concepts. All right, we usually associate them the same thing. We hear announcements in baseball that a pitcher throws a baseball at a velocity of 98 miles per hour or speed 98 miles per hour. We associate the same ring. However, speed does not consider direction, hence why we use distance, whereas velocity does consider direction, hence why we use displacement. So velocity depends on 2 factors, not only the speed, but also the direction. An example illustrating the difference between speed and velocity is if we look at this diagram right here, okay? If we have an object that's heading 2 meters per second to the right and another object is heading 2 meters per second to the left, they're both going to have the same speed, 2 meters per second, but they will have different velocities, okay? The velocity vector for the object heading to the right is going to be positive 2 meters per second, the positive indicating that we're moving to the right, and the 2 meaning that we're doing so at 2 meters per second. This vector right here, pointing to the left, indicates to us that our object's velocity that's heading to the left is -2 meters per second. A stark difference from its speed of 2 meters per second. The negative indicates to us that we're heading towards the left, and then the 2 indicates that we're heading towards the left at a rate of 2 meters per second. So as a quick check for understanding, suppose that it takes object C 30 seconds to complete its path. What would be the speed of path C, and what would be the velocity of path C? So in this case, if we recall, okay, speed is going to be distance divided by time, okay? So in this case, if we recall, the distance traveled for object C in this case was 12 meters. So we're going to have a speed of 12 meters divided by 30 seconds, which is going to give you 0.4 meters per second for your speed. Okay? Now if we calculate out the velocity, we now need the displacement instead of the distance traveled. So our displacement for C is going to be 8 meters, from 2 to 10 meters. Okay? So in this case right here, object C is going to have a velocity of 8 meters divided by 30 seconds, which is going to give you about 0.267 meters per second, if I recall correctly. And then we have some more problems for object D, if you care to work through, that also have solutions in the slide solutions. So next we look at defining acceleration. People typically think of acceleration as strictly speeding up. Okay, we hear things accelerate, they go faster, they're speeding up. However, the official definition in physics is a little bit more subtle. Acceleration is defined as the change in the velocity of an object. Acceleration has units of meters per second squared. So there are 3 different ways that an object can accelerate based off this definition right here. The first off is the most obvious, speeding up, okay? The second one is we can slow down, okay? So we can change the speed of an object by decreasing the speed, okay? And since we're decreasing the speed, we're also decreasing the velocity. Remember, velocity depends on speed and direction. So as a result, we can slow down. That's the second form of acceleration. So we hear in everyday life that an object decelerates when it slows down. However, there is no such thing as deceleration in physics. There's strictly acceleration by slowing down. Acceleration is the same regardless of whether you're speeding up or slowing down. It's just different forms of acceleration. And then lastly, we have changing direction, okay? So acceleration, if you're changing direction, okay, that's considered a form of acceleration because velocity not only considers speed, but also considers direction. So essentially we can think of acceleration as any time you have a change in motion, whether you're changing direction or whether you're speeding up or slowing down. Okay? A way to think about change in direction, because this is quite difficult to think about, is like if you've ever been in a car on a roller coaster, or on a roller coaster goes around a curve, you feel your motion change, you feel yourself get swung outward as that roller coaster car goes around the curve. So that's an example of acceleration because your motion is changing. Specifically, it's called centripetal motion, as we'll learn down the line in this course when we get to centripetal motion. Okay? So the conditions for accelerations, for speeding up and slowing down and changing direction, okay? So, speeding up, slowing down, changing direction depends on the relative sign of your velocity and acceleration vectors. So if your object, if you're speeding up, your velocity and acceleration vectors will be in the same direction. So for example, for a car that's heading to the right and speeding up, its acceleration will also be to the right. On the flip side, if this velocity was to the left and our car was speeding up, acceleration will have to point in the same direction, which means acceleration would also be pointing to the left. The idea here to think about is when you're speeding up, it's like pressing on the accelerometer of your car. So the acceleration is going to push your car forward to cause it to speed up, so it's going to push in the same direction. That's a more little subtle notion, and that's going to be a topic we better explore when we get to what's called forces in Unit 3. Okay? Now, for slowing down, all right, if pushing on the accelerometer is like pushing the car forward to cause it to speed up, slowing down, okay, is like pressing on the brakes. And when we press on the brakes of a car, it's like the brakes are pushing against the car to slow us down. So in the case when we're slowing down, acceleration will be opposite of your velocity. So if my car is heading to the right, it will have a positive velocity, a rightward velocity. But if it's slowing down, its acceleration will be in a negative direction, to the left. Vice versa, if my car is now heading to the left and slowing down, the acceleration will be heading towards the right, because acceleration will be pushing against the car to slow us down. And then lastly, if we have a change in direction, the acceleration is going to be perpendicular to the velocity. Acceleration will always be perpendicular to the velocity when we're changing direction. The idea here is that when our car is, or our object wants to change direction, okay, our object wants to head on a straight line. What we'll learn this is called Newton's first law. We call it law of inertia. Objects tend to want to head on straight lines at a constant speed or constant velocity. So in order to change our object's motion, let's say we want it to start turning down like this, okay, we're going to have to push our car or push our object in the direction that we want it to head, strictly in the downward direction. So in this case right here, our acceleration has to be pointing downward in order to get our car to start moving downwards, okay? And then acceleration, here's the equation for acceleration. We don't really need the equation for acceleration that much because it's going to be supplanted by the much more useful form of kinematic equations down the line in this unit, but for right now it's a good thing to see. So acceleration is your change in velocity per unit time. So case of acceleration, slowing down, speeding up, and then the big one, orbits. So orbits are in fact cases of acceleration. We don't think of the moon or the ISS as accelerating because they tend to move at constant speeds. However, they are accelerating because they're always changing direction on their orbits, okay? So the last way we can visualize the motion of an object is through what we call motion diagrams, which are essentially how speed trap cameras at traffic stops work, okay? So the idea behind a motion diagram is it's kind of like a strobe light. So if you look at a strobe light, you have a snapshot of an object that each time the strobe light flashes gives you a snapshot of the object over a certain time interval, okay? And based on what you see of the strobe light happening, you can interpret what's happening to the object's motion. So for example, with this right here, if we look at the strobe light, we have these different snapshots of a person at different seconds. We see that as the snapshots in time grow, we see that the distance a person is covering is also growing. So this would indicate to us that our person is speeding up. Likewise, in D, we can see that as our snapshots continue, we can see a distance our person covers decreases, indicating to us that we're slowing down. And then lastly, in B, we can see we cover the same distance over each snapshot interval, indicating to us that we are moving at a constant velocity. So the idea behind motion diagrams is that if you're speeding up, the distance between intervals will increase, like we have in C. If you're slowing down, the distance between intervals will decrease, like we have in D. And if you're moving at constant velocity, the distance will remain the same, okay? Lastly, we come to instantaneous versus average velocity. So, Suppose I were to cover 120 miles in 2 hours on a straight, flat road. No turning around, no hijinks or anything like that with the first question we face this lesson. I'm just heading straight on a road for 200 miles. What would my average velocity be? My average velocity would be 120 divided by the time it took me to travel as 120 miles. Let's say that's 2 hours. So that would give me an average velocity of 60 miles per hour. However, is it true that I'm always heading at 60 miles per hour on this trip? Well, when we think about it, that's not exactly true. There could be points where I'm heading faster than 60 miles per hour and points where I'm heading slower than 60 miles per hour. But so long as those points average out to 60 miles per hour, my average velocity will be 60 miles per hour. So this defines the difference between instantaneous and average velocity. Okay? So average velocity is a change in displacement over a certain time interval. Say, for example, Mr. Heffley travels 80 miles in 2 hours. I used 120 miles earlier, but it's the same idea. So his average velocity would be 40 miles per hour. But then we have instantaneous velocity, which defines how much my position is changing per second at a single moment in time. Hence why we call it instantaneous velocity, because it measures how much our displacement is occurring at a single instant in time. So, for example, at one point in his trip, Mr. Heffley was traveling at 60 miles per hour. Okay, so it's not exactly true. I always have to be heading at average velocity over the entirety of my trip. Average velocity, for those of you all who are math aficionados, is the physics application of the average rate of change that you may have learned in Algebra 2. For those of you all who are in calculus, instantaneous velocity is the physics application of the derivative. If you're wondering how to determine the instantaneous velocity in your car, well, that's where you would look at the speedometer. The speedometer tells you how fast you're moving at any specific one moment in time. And lastly, we have our check for understanding. True or false, an object that has a constant speed cannot be accelerating. Cite an example to justify your claim. So as we've talked about, people would tend to say that this is true because a constant speed means we can't speed up or slow down. However, we got to remember that velocity consists of not only speed but also direction. So if we're accelerating, it could be that we have a constant speed, but we could also be changing direction. So the object could have a constant speed but be changing direction. So as a result, the velocity is changing, and thus our object would be accelerating. And this covers our lesson for 2.1, the basics of motion.